Assalamualaikum and hi to all. So this is part 4 video for chapter 3 gas turbine cycle. So in this video I'm going to explain two subtopics. One is the methods to improve performance and the second one is Brayton cycle with regeneration. Methods to improve performance. Okay, method to improve performance of gas turbine. So as you can see, this is the efficiency of the gas turbine, calculation of the efficiency of the gas turbine from work net divided by Q in. So from this figure, we know if we increase the work net or we decrease the Q in, we can increase the Brayton cycle. So efficiency of the Brayton cycle. First, we look into the decreasing the Q in. As you can see here, Q in is being decreased and this is being called as the regeneration. And this is the actual cycle of the Brayton cycle with regeneration. As you can see here, this is the regeneration section where we increase the temperature of state 2 uh, close to the exit temperature of the turbine, which has the higher temperature compared to the compressed air at state 2. Another method is we increase the work net input of the system. So as we all know, work net is calculated from work out minus work in. So first we can decrease the work in from the compressor by using multi-stage compressor with the intercooler. And this is the diagram of the actual system of the Brayton cycle with the multi-stage compressor with intercooler. As you can see from the state 1 here, and this is the multi-stage compressor C1, compressor 1 and compressor 2. And as you can see here, this is the intercooler section. From state 2 goes into the state intercooler and the output of it is state 3. Another method is we increase the work uh, in or work out by the turbine by using multi-stage turbine plus reheating. So as you can see in the state 6 here, this is the state 6 and this is the turbine number 1 and this is turbine number 2, which is the multi-stage turbine. And here is the reheating section. As you can see from state 7, it goes into the heat exchanger or reheating section and the output of it is state 8. So this is the way to improve the performance of gas turbine. Either you increase the work net out or you decrease the uh, Q heat input to the system. Brayton cycle with regeneration. Brayton cycle with regeneration. So, as already explained in the previous slide, we can increase the efficiency of the Brayton cycle by decreasing the heat input with regeneration. So, as you can see here, when we increase the heat input here, we also decrease the fuel consumption or fuel input into the system. And the temperature difference also from state 3 minus state 5 also will decrease. And the regenerator or the recuperator actually is preheating the air entering the combustion chamber. So this is the actual diagram of the Brayton cycle with the open system without the assumption. And as you can see here, we have the regenerator here, which preheat the air from the exhaust air at the turbine here, state 4. We will preheat the output compressed air at state 2. We'll change it into state 5 with the higher temperature. However, at the same pressure. So this is the actual open cycle of Brayton without regeneration. And as you can see here, actually we put the heat exchanger or the regenerator is actually a heat exchanger which reheat the from the Q out. It will reheat the air at the state 2 and it will increase the air of the state compressed air state 2 into state 5 or temperature at state 5 here. And Q here is called the Q regeneration. And this is the closed cycle, simplified closed cycle, Brayton cycle without regeneration. And this is the TS diagram. As you can see here, we have regeneration here, which is from the exhaust gas of the turbine. It will reheat the temperature of state 2 into state 5A or 5 prime. 5A is the actual temperature. 5 prime is the maximum temperature can be regenerated. And from here, Q safe is equal to the Q regeneration. So the Q out, actually, part of the Q out is transferred or is given to the state 2 to increase the Q in. So from the temperature regeneration actual, it should be lower than the temperature of the exhaust of the turbine. As you can see here, T5 prime, T5A should be lower than T4, and the Q regeneration actual, which is the heat input regeneration actual, is equal to H5A minus H2. H here is the enthalpy, and T regeneration maximum, which is the T5 prime A, is equal to T4, and Q heat regeneration maximum is equal to H5 prime minus H2, and it is also equal to H4 minus H2. As you can see here, H5 prime here, value of H5 prime is equal to H4 because it is at the same temperature. So the regenerator performance, we can calculate the regenerator performance from the effectiveness, which is given by this equation, which is equal to Q regeneration actual, which is heat input from the regeneration actual divided by heat input regeneration maximum, can be calculated, which is 5 prime, and we can calculate also H5A minus H2 divided by H5 prime minus H2, or it is also equal to H5A minus H2 divided by H4 minus H2. H here is the enthalpy of the state. And based on the call as standard assumption, we can calculate the efficiency of the regeneration, which is equal to 1 minus in the bracket T1 divided by T3 times the compression ratio with the power of K minus 1 divided by K, which is as shown in this slide. And we also can use the temperature to calculate the effectiveness, which is T5A minus T2 divided by T4 minus T2. And from the this system, let's say we can increase the efficiency of the system, and we can decrease the fuel. However, to get the optimum or higher efficiency or effectiveness, we will need a larger regenerator, which are not cost effective throughout the system. So in normal cases, the efficiency or the effectiveness of the regenerator is less than 0.85 or less than 85%. Brayton cycle with regeneration. So, as already explained in the previous slide, we can increase the efficiency of the Brayton cycle by decreasing the heat input and the fuel consumption. And also we can decrease the temperature difference, which is the T3 minus T5. Now first we look into the system without regeneration. This is the open cycle, which is the actual diagram of the Brayton cycle, and this is the closed cycle, which is the simplified Brayton cycle. And as you can see at the state 5, or temperature at state 5 is equal to 20 degrees Celsius, and temperature at state 3, which is in the open cycle, after the combustion chamber CC, which is the 100 degrees Celsius, and the closest cycle after the heat exchanger with the Q in is equal to 100 degrees Celsius state 3, and the temperature difference here is the 80 degrees Celsius, and Q input, which is heat input into the system, is equal to 100 kilojoule per kg. Now we look into the system with regeneration, and this is the open cycle with regeneration. As you can see at the state 6 here, we have regeneration here, and For the closed system, we have the heat exchanger with the Q out and also Q regeneration here. So since we have the regeneration, the temperature at state 2, which are previously at 20 degrees Celsius, now since we have the preheat from the heat exchanger, we have Q regeneration from the exhaust air of the turbine. It increased the temperature at state 2 from 20 degrees Celsius into 50 degrees Celsius. And as you can see, and the temperatures at the state 3 after the heat exchanger and also combustion chamber still at 100 degrees Celsius. So from this, we know the temperature difference of the state 2, state 3 minus state 5 is equal to 50 degrees Celsius, and the heat input should be less than the heat input without the regeneration, because we already have preheating section before the air enter the combustion chamber or the heat exchanger at state 5 to state 3. Brayton cycle with regeneration. So now we look into the effectiveness. Let's say we have a 100% effectiveness, which is the maximum condition. And this is the open cycle of the Brayton cycle, and this is the closed cycle of the Brayton cycle, which is the simplified of the actual cycle. And let's say we have temperature at state 4 is equal to 500 degrees Celsius, as you can see in the figure, and 100 kilojoule, which is heat out from the turbine is 100 kilojoule. The regenerator able to transfer heat effectively so that the temperature at the inlet of the combustion chamber heating section is same as the temperature at the outlet of the turbine. So this is what is meant by the 100% effectiveness, meaning that the temperature at state 5 will be 500 degrees Celsius, and the 100 kilojoule can be transferred 100% to the preheating of the state 2 to state 5. So for the system which has effectiveness less than 100%, as I show in this figure, the actual condition, which is the actual condition. So this is the open cycle of the Brayton cycle, and this is the closed cycle of the Brayton cycle with the assumption. And the temperature at state 4 is equal to 500 degrees Celsius, and the heat output from the turbine is 100 kilojoule, and the regenerator is less effective to transfer heat, cause the temperature at the inlet of the combustion chamber heating section lower than the temperature at the outlet of the turbine. So in this case, the temperature from the preheating or the regenerator is not 100% effective. So the temperature of state 2 cannot be increased to be the same as the temperature of the output of the turbine. So in here, the temperature at state 5 is 300 degrees Celsius, which are less than the temperature at state 4, 500 degrees Celsius. So this is the difference between the maximum heat regeneration and also the actual regeneration. Please keep this in mind and make sure you understand the concept of maximum and also the actual condition. So for your attendance, please uh, explain in brief the difference between maximum and also actual condition. So the T regeneration maximum, which is the T5 prime, is equal to T4, and Q regeneration maximum is equal to H5 prime minus H2, and it also equal to H4 minus H2. However, in the actual condition, the temperature regeneration actual T5A actual is less than T4, and the Q regeneration actual is equal to H5 prime A H5A minus H2. So H here is the value of the enthalpy. Closed cycle gas turbine plant, Ravensburg 1956 regeneration. So this is the complete diagram of the gas turbine plant with regeneration. And this is all the equipment in the diagram. A is the high pressure side blow off valve, bypass valve, compressor, which I put in the blue color there, and intake air throttle device, exciting machine, combustion air blower, regenerator, makeup air compressor, H2H1, cold mills, air heater combustor, there is the air heater or the combustor, starting motor, induced draft fan, pressurized air storage, turbine, and reduction gear, pre-cooler, recuperator or regenerator, which I put in the green dotted rectangular, and intercooler here. Now we look into the working diagram. As you can see in the blue arrow here, this is the blue arrow. It goes into the turbine, it goes into the compressor. This is the movement of the air, and goes into again into the compressor, and it goes into the preheat or preheating section or the heat exchanger, and the preheat air will goes out of the system, and it is in the preheating section, the air is being heated up by the uh, exhaust air of the turbine, as you can see the red arrow there, and we reheat the heating the air from the compressor, and the preheat air from the compressor will goes into the combustion chamber, as you can see in the green arrow, and the output of it is the high temperature. It goes into the turbine, and the exhaust of it will reheat the uh, compressor air from the compressor, which I already explained before, and the air will goes back into the compressor or inlet. So this is the complete cycle or complete process of the gas turbine plant with the regeneration. Regenerator and recuperator. So this is the actual recuperator, and actually it is the heat exchanger of shell and tube heat exchanger. And so this is the actual cross section of the front view and also side view of the recuperator or the heat exchanger. And inside of it is the corrugated strip fin tubes. So why it is being called a shell and tube? Because inside of it we have tube, and the outside of it is shell. So that is why it's being called uh, shell and tube heat exchanger. And the air does not mix between the hot air and the cold air. It does not mix. So from the compressed air, it goes into the tubes, as you can see the blue arrow there, and goes into the system. And now the hot air is coming from the turbine. It is come from the different direction and goes into the shell side, and will cross here there, and then will transfer heat into the compressed air from the compressor, and will preheat the air and turn to be green arrow there, and we move out to air heater turbine. So this air is slightly the temperature of the air is higher than the compressed air from compressor. Now the hot air from the turbine, it goes out of the shell of the heat exchanger. So this is the complete system of the heat exchanger, how the heat from the turbine transfer heat to the compressed air from the compressor. This is the end of part 4 for chapter 3. Hopefully you enjoyed this video, and thank you.